This video, we're going to talk about section 3.2, determinants and elementary operations. Elementary row operations for determinants is what we're talking about, though these elementary operations don't just work on rows, they also work on columns of determinants. So let's go ahead and start by talking about the three elementary operations that would simply be row operations for regular matrices, but what happens when we do these row operations or column operations to a determinant. So the first one says when row or column B is obtained from, and it needs to be the same thing, row or column have to be the same. A, by interchanging and I'm going to just add a word here. I'm going to say adjacent rows or columns of A, then determinant of B is equal to the opposite of the determinant of A. We want to, in a determinant, swap rows or columns that are right next to each other. And we keep doing that until we get the row or column where we want, but each time that we swap adjacent rows or columns, then we change the sign of the determinant, but you don't want to move it more than one row or column at a time with this formula, because then you have to worry about how many columns away did you move it and so on. So just one row or column at a time, just swap places with adjacent rows or columns. All right. So property number 2, when B is obtained, again, B is a row or column. When row or column B is obtained from row or column, and they have to be the same. Row, it's row, column, it's column. A, by adding a row of A to another row of A, then you have not changed the determinant. Okay. And then the last property, and you can do that as many times as you want to add that row. So you can add a constant multiple of a row, a non-zero constant multiple of a row to another row. But just if you add any row, and then you can keep doing that and not changing it. So you can do that along with number 3. And number 3 says when row or column B is obtained from row or column A by multiplying by a non-zero constant, that we're going to call C. Determinant of B is equal to C determinant of A. So if we have an n by n matrix, it has to be a square matrix that we're taking the determinant of. We want to multiply everything in the matrix by C. Then when we factor out here, we're going to get C to the n determinant of A. That'll be something we may use in a little bit if we have n rows or n columns and we want to take the common factor of C out of all of them. It'll be C to the n because the C comes out for each row or column, unlike with regular matrices. When we factored out a C out front of the matrix, it meant we were factoring that out of everything in the matrix. This just comes out of a single row or column to affect the determinant. So that's a big difference there. Whereas row swaps didn't affect the matrix really at all, it does change the sign of the determinant. And like in matrices that adding constant multiples of a row to another row is not going to change what the determinant is. So that will help us out. All right, let's go ahead and get started with some problems now that we know the properties that we're going to be working with. With number 1 here, and it says determinant of 2, -6, 1, -3. That needs to equal to 0 because the first row here is 2 times the second row. So if we would take the difference here, if we would subtract 2 times row 2 from row 1, we would get a row of zeros. Anytime there's a row of zeros or a column of zeros, we're going to get a determinant of 0. So the first row is 2 times the second row. If one row is of a matrix, of a determinant, is a multiple of another row of the determinant, and I can say column here as well, the determinant is 0. Because it would produce a row or column of zeros that would force a 0 determinant. So let's look at number 3. And it says 1, 4, 2, 0, 0, 0, 5, 6, 7, and that's 0 because the second row is all zeros. If one row or column of a determinant is all zeros, the determinant is 0. That'll make more sense when we do expansion with minors and cofactors here in a little bit. So go ahead and look at number 5. And it says that we start off with 1, 3, 4, -7, 2, -5, 6, 1, 2. We want to show by properties that that's equal to a negative determinant of 1, 4, 3, -7, -5, 2, 6, 2, 1. And we swapped adjacent columns there. So we swapped columns 2 and 3. So by property number 1 that we talked about earlier, then determinant of this matrix that we attained by swapping the rows is equal to the opposite of the determinant of this is the opposite of the determinant there that was before the row swap. So they're opposites of one another. So that was just property number 1 that we already talked about. Let's go ahead and look at number 11. And it says -10, 5, 5, 35, -20, 25, 0, 15, 30. And we're going to take a 5 out of everything. There's 3 rows, 3 columns. That's 5 cubed. It's -2, 1, 1, 7, -4, 5, 0, 3, 6. And that's property 3 that we already talked about. So I'm not going to quote property 3 again. I just say that 5 was property 1 and 11 is property 3. Let's go on now to number 23. Tells us to use either elementary row or column operations or cofactor expansion to find the determinant by hand. And then you can use a software program like the Desmos matrix calculator or your TI-84 calculator to verify your answer. But I'm just going to do the by hand part here. So 5, 1, 0, 1, 1, 0, -1, -1, 2, 0, 1, 2, -1, 0, 3, 1. So a fun property about determinants, and we'll use this later, is that if I can force a upper triangular determinant where I have zeros below the main diagonal and all my non-zero numbers are above, that's an upper triangular matrix that I can take the determinant of, or a lower uh, triangular matrix where all the non-zero numbers are down here and the upper part is zeros, then the determinant is just the numbers along the main diagonal. So this one's not going to be too hard, I don't think, to get that. I'm going to see. Let me go ahead and use this 1 to get rid of this 2 before I get rid of the 1. So I'm going to get that's -2 row 2 plus row 3 produces a new row 3, and this keeps the same determinant. 5 1 0 1 1 0 -1 -1, and then 0 0 3 4 and -1 0 3 1. So now I can row 2 plus row 4 makes a new row 4, and that's 5 1 0 1 1 0 -1 -1 0 0 3 4 0 0 2 0, and I've got negative row 4 plus row 3 makes a new row 3. Five 1 0 1 1 0 -1 -1 0 0 1 4 0 0 2 0. All right, so I'm going to pull the 2 out from row 4. Give me a second to deal with that. Let's see, -4 row 2 plus row 1 to give me a new row 1 first. And give me 1 1 4 5. Then I've got 1 0 -1 -1 0 0 1 4 0 0 2 0. I've got negative row 1 plus row 2 gives me a new row 2. It's 1 1 4 5 0 -1 -5 -6 0 0 1 4 0 0 2 0. I've got pull that out here. Let's get a 0 here by -2 row 3 plus row 4 gives me a new row 4, and that is 1, 1, 4, 5, 0, negative 1, negative 5, 6, 0, 0, 1, 4, 0, 0, 0. And then this is negative 2 plus that, that's negative 8. And that's enough now for me to say my answer is 1 times negative 1 times 1 times negative 8 is 8. And you can verify that with your calculator. So as soon as I got a lower triangle or a upper triangular matrix there, I was good. Let's go ahead and do number 27. And it says negative 2, negative 1, negative 1, 1, 3, 2, negative 6, 3, 3. And my instructions tell me to use elementary row or column operations to find the determinant. Do not use the calculator this time. So I'm going to go ahead and say that this has to be equal to 0 because row 3 is equal to negative 3. This is 27, right? This is a positive 2. It's equal to a negative 3 times row 1. So anytime that, and I'll work it out here, but this is going to be negative. So this is going to be 3 row 1 plus row 3 to produce a new row 3 is 2, negative 1, negative 1, 1, 3, 2, and then I get a 0, 0, 0. And anytime that I have a row of zeros, that's going to be 0. So that was 27. Going to jump all the way ahead now to number 41. And the instructions here say to find the determinant of the elementary matrix, and it has a K in it. Assume that K is not going to be equal to 0. So 41 says 1, 0, 0, K, 1, 0, 0, 0, 1. So let's use minors and cofactors here and expand on row 3 would be my ideal choice, since it doesn't matter. We could use, actually let's use row 1, which just eliminates the need for the K, because the K is going to be there in 1. So I don't need to worry about K at all if I do that. So 1 times 1, 0, 0, 1 minus 0 times K, 0, 0, 1 plus 0 times K, 1, 0, 0. So this is 0 and this is 0. They'd be 0 because of those 0 constant multipliers there. So 1 times 1 times 1 is 1, minus 0 times 0 is 0. 1 times 1 is 1. So my answer is 1. Number 45 asks me to find the determinant for these matrices. 45A is the determinant of cosine theta, sine theta, negative sine theta, cosine theta. This is going to be an important one in differential equations if you take that, because the derivative of cosine is negative sine and the derivative of sine is cosine, this forms a special kind of determinant that we talk about where we start off with functions and then the subsequent rows are their determinants. So cosine times cosine is cosine squared theta. And then we have minus, and then sine times negative sine is negative sine squared theta. So we come up with cosine squared theta plus sine squared theta is going to be 1 by the Pythagorean identity. B is the determinant of sine theta, and then 1, and then 1, and then sine theta. So we want sine times sine is sine squared theta. And then we have minus 1, which is the opposite of 1 minus sine squared theta. So that's the opposite of cosine squared theta. That's it for this video. There's another suggested problem, but it's a guided proof. And I don't really see any advantage to going through the guided proof for you when it tells you every step to take. So that's number 47. Go ahead and do that one. If you have any problems with that one, maybe ask your instructor for some help with it. But basically, it's the proof of property number 2 that we talked about earlier at the beginning. And this just gives you some idea of what a rigorous proof is. You haven't really done a lot of these, but prove that that works for all determinants that are square, regardless of their number of rows and columns that they have. Just remember, you're dealing with a square matrix. That's going to be an important part of that proof later on. So that's it for this video. We'll come back next time and we will talk about 3.3, which is going to be properties of determinants. So I'll see you for the next video.